This lesson deals with Supplemental Problem 2.7. You can find this problem in the ECE302 ebook in the Chapter 2 Supplemental Problems, starting on page 12. Let's do the example on pages 16 to 19 of the Chapter 2 lecture notes with PSpice at a frequency of 1 kilohertz using a 470 microfarad capacitor for each of the capacitors and a 1N4001 diode. Compare your simulation results with your hand calculator results. Here's a schematic that we had in Chapter 2. The first step with a SPICE file is to number all the nodes. Ground node is labeled 0, and then I just picked 1, 2, 3, 4, and 5. You can also use letters or expressions. The value of the capacitors were 470 microfarads. Diodes are 1N4001. This resistor was 100 ohms, this was 2000 ohms, and this was 2000 ohms. And our input was a 10 millivolt sine wave, but let's now specify this to be at 1 kilohertz. What's the magnitude of the impedance of the capacitor at 1 kilohertz? Well, we can go back to ECE302, and the impedance of a capacitor is 1 over j omega c. The magnitude would be 1 over omega, which is 2 pi f, times the value of c, and that is 0.339 ohms. And that's much, much smaller than the resistors that are hooked up in series with it. We could think of this capacitor at 1 kilohertz as if it were a short circuit. Let's review how to write a SPICE file. Every SPICE file must begin with a title. I'll call this example. And it has to end with a .end. This is for the line editor version of PSpice, or SPICE. We'll talk about the schematic capture version in a later course. If you want to comment about this particular circuit, you can do that by using an asterisk in the first position. Here I'm going to call this a voltage-controlled attenuator. It just ignores any line that begins with an asterisk. Voltage sources begin with V. This is called Vin. It's between a plus node and a minus node. Plus is first, minus is second, so 1 and 0. This is a sine wave, whose average value is 0, whose peak value is 10 millivolts, and whose frequency is 1 kilohertz. In PSpice and SPICE, the letter M was only uppercase in the original program, and that meant milli, and if you wanted mega, it was just MEG. Capacitors and resistors don't really have a polarity in the SPICE program, and so you can pick any node as the first node and the second node. In SPICE, it's going to be considering this as the plus and the minus if you pick this first and this second, like I did over here between 1 and 2. What that's going to mean is that if you ask for the current in this element, it'll be from nodes 1 to 2. And the value is 470 microfarads. The resistor R1 is between two nodes. I just picked 2 first and then 3, 100 ohms. The resistor R sub C is up here on top. It's between 5 and 3 or 3 and 5. Pick it any way you want to, and it's a value of 2K. This capacitor is between 3 and 4, value of 470. There's a battery between nodes 5 and ground. Plus node first, minus node second. That has a value of 2 volts. We'll run the simulation again with 10 volts. That was the two values of the battery that were in that example in Chapter 2. There's a load between nodes 4 and ground of 2K. And there's a diode between nodes 3 and ground, 3 being the anode and 0 being the cathode. And then we're going to use the model that we developed in Supplemental Problem 2.5. Semiconductor begins with dot model. Here we have a name, and I'll make the name the part number. What is it? It's a diode. We'll later change this for transistors. It has a value of I sub s and eta, as we talked about in the lecture notes. Then we got to decide how many cycles we want to plot. So we have 1 kilohertz here. Well, the reciprocal of that is 1 millisecond. If we did 4 cycles, that would be 4 milliseconds, and that's how I picked this number right here. I want to have at least 200 data points on the screen, so I'm going to divide this number by 200, and that's the value of 20 micro. We're going to start the simulation at 0, and then this fourth number is very important that you specify it to be equal to the print step. If you look back in Chapter 8 of ECE302's ebook, between pages 26 and 30, you'll see that if you don't do that, you get a lot of distortion in the waveform. There's some defaults that are set here from the early versions of the program that can cause what appears to be errors. Okay, so we're going to run this file like we did in the lecture notes, and then take a look at the output. See where the output is here. It's from node 4 to ground, and I'm also going to plot the input. It's on the following page. I plotted node voltage 4 and node voltage 1. Node voltage 4 is the output, and node voltage 1 is the input. Here's my 10 millivolt sine wave, and I've got 4 cycles. And what's coming out across the 2K load is something that's much smaller. I forgot to mention in the previous page we had a command called .prob. What that is it's collecting all voltages and all currents in your simulation, so I can ask for any voltage or any current. Then I varied the power supply, ran the program again, but now with a value of 10 volts for V sub C. And you can again see that my input is still the same, 10 millivolts peak, 20 millivolts peak to peak. And you can see now my output's a lot smaller. As I changed that voltage, I was changing the voltage division in the circuit. Take a look at hand calculating these results. I forgot to mention on page 12 that there was a command called .op that's asking for what's called the operating point. It's going to give us the DC and the AC parameters of our semiconductors, in this case the diode. And I just printed out this part of the output file. It said for our diode D1, we only had one diode in our circuit. It has a value of current at 709 microamps and a voltage across it of 0.582. It's again using the Shockley equation. And we'd figured out an equivalent AC resistance in the lecture notes, and it calculated that to be 60.9 ohms. Take our circuit on page 12. We replaced every component with its AC model. This is an AC source, and this is a battery which we showed in the Chapter 2 lecture notes. Looks like a short circuit for AC. And the reason for that is that the impedance AC-wise is the change in voltage over the change in current. Because this is a constant voltage, there's no change in voltage. This was a resistor, and a resistor, which are the same for AC and DC, but our capacitors, because the impedances were so small in magnitude at 1 kilohertz, we could think of them as short circuits. And then our diode looks like a resistance at a point. We're just going to analyze this resistive circuit. What I've got is a voltage divider. I've got 60.9 in parallel with 2K in parallel with 2K. Voltage divided with 100 ohms. All this in parallel is going to be smaller than the smallest resistor, so 57.4 seems reasonable. And then we can just form this over here, and we get a result of 0.3647 times the input. But our input is a 10 millivolt sine wave at 1 kilohertz. Multiplying this out, I get 3.647 milli times the sine of omega t, and the peak-to-peak value is twice this. I used the cursor to get the peak-to-peak value, and that was 7.2984 millivolts. So these two numbers are very close to each other, really within the default accuracy of PSpice, or SPICE, which is 0.1%. Take a look at what happens now when we change the voltage from 2 volts to 10 volts. Run the program again now with the voltage V sub C equal to 10 volts. Have a new output file, and again grab the parameters from the operating point that said now that this diode was sitting at 0.663 volts and a current of 4.67 milliamps, and then it calculated the effective resistance using the slopes actually of 9.25 ohms. Go back to our original schematic and we replace every component by its AC model. Here's my AC source, my resistors that were here, and now my equivalent resistance of the diode, and that my capacitors look like very low impedances, basically short circuits. And again, I've got a voltage divider to analyze. I only have 9.25 ohms here in parallel with 2K and 2K, and that's a little bit smaller than 9.25. It's 9.165. That gives me a voltage divider with Vn of 83.96 milli. Multiply that by a 10 millivolt sine wave, and you wind up getting 0.8396 milli times the sine of omega t, where omega is 2 pi f, or 2 pi 1 kilohertz. And that has a peak-to-peak value of twice this, which is 1.6792 millivolts. Then the simulation I also measured with the cursors the peak-to-peak value, and again you can see these are very, very close to each other. As I mentioned before, the default accuracy of SPICE is 0.1%, and this is much, much smaller than that. It's about 0.006%. What's happening here is by changing a DC voltage, I can control a voltage divider. Instead of having a pot, rotating a pot to change something, I could send a remote signal and be able to convert that to a DC voltage, we'll see later in the chapter. I could use that to actually change the value of something without mechanically or physically having to turn a knob. And this is supplemental problem 2.7.